Welcome, ladies and gentlemen. Today, with this presentation, we're going to look into thin film encapsulation for flexible OLED and its optical properties. This presentation has been prepared by Meyer, Netherlands, BV, and the narrator will be Luca Gautero. A view of the agenda. We are going to have an introduction. We're going then to make clear what are the goals and the background. We're going then to make simulations, and so there will be assumptions and description of the optical structure. This will lead then into results and discussion. We're going to have a look on the reflection, its transmission, and the absorption over the visual spectrum, and we will have some consideration on the angle of emission. This will then end in the conclusion. What better introduction than by starting to say who we are and what we do. We are Meyer, Netherlands. We are equipment manufacturer, and we have specialty in PCVD and inkjet printing. We can create pilot tools with dimension up to generation 2.5 and production tools with dimension up to Gen 5. These are then proposed as a fully integrated solution between PCVD and inkjet printing and automation. We have been working within triangle collaboration. We collaborate with a host center for what concern the device know-how and the process research, and with a functional inks supplier for aspects like planarization and tortuous path creation. This together will then lead to the creation of OLED barriers which deliver high performance and are reliable protection for moisture sensitive devices. We see here an example on the left of an OLED device, and on this kind of sample we demonstrated a WVTR, so a water vapor transmission rate, in the range of 10-6 grams of water per day per square meter. As you can see in this picture, the device is flexible, so what we have been doing is represented here in a very simple schematic. You see a substrate which will be flexible, and then you see a transparent barrier below the OLED and a transparent barrier on top of the OLED. From the scheme that we have seen, let's move more in detail to have a look at what these barriers mean. Well, we have said that there is a foil at the bottom which is flexible and transparent, so a PET or a PN would be suitable. And then we start putting an organic coating for planarization by means of inkjet printing, and on top of that we put a silicon nitride by PCVD. This combination of an organic and inorganic will be referred as a diet, and we repeat the diet. At this moment we will have a barrier for the bottom that ensures the water vapor transmission rate that we want, so therefore reach this 10-6 gram per square meter per day. We can place here an OLED, and on top of the OLED we will need again a barrier which will be again made out of two diodes. We have seen the structure of the barrier, and now let's have a look at the equipment that makes this possible. So here we have a picture of a realized tool, and here a scheme of what this tool can contain. So we start from an automatic substrate handling to have the incoming substrate being transported in the tool. Here, for the sake of showing better what is contained, we are not showing the inert tool containment. So the substrate can then be transported to an inkjet printing module and a PECVD module by means of a robot. This will help to minimize timing between the printing and the silicon nitride coating. Then, when the sample will be ready, it will be returned back to the lot lock, and from the lot lock can be interfaced to the outside world or other tools. Such a machine can have substrate up to Gen 2.5. Is a coupling, as we said, of a PECVD module and an inkjet printing. These are namely Flex LT and IP410. The loading is automatic and the unloading as well. We have also a sketch of the inert boxes, and thanks to this robot handling, it is possible to have a single diode and multiple diode to make top or bottom barriers just by changing the automatic process that is instructed to the tool. Let's talk about the goal. What we want to do is to detail the optical performance of a barrier on an OLED. The OLED itself, as we see here depicted, similar to the previous slide, will have an OLED at the middle, and this OLED will shine toward the bottom. We are assuming here that we have an aluminum barium cathode, so of course this will obscure any emission towards the top. So the light will go towards the bottom. It will leave the OLED structure, in this case a simple P-LED on top of P-dot, and it will go through the bottom barrier. The detail on the performance will help us to avoid risk of having optical devices underperforming, especially when migrating from classical glass encapsulation to a full thin film encapsulation. The advantage of going towards a full thin film encapsulation will be the bendability of the devices, as we see here in this picture. The light is shining and the foil has been bended, and the device is not affected by it. The background to perform all of these analyses is the availability of an optical calculation platform, which is OptiCalculate from Sandbergen and Zollingen, and is a module in MATLAB. The optical properties of a material are also needed as input. When available, these are measured data, otherwise they are taken from tabulated values. And then we have the structure that we have seen before, which is given. So we will use a double diode bottom barrier as an optical system. To illustrate how the simulation will be shown, let's see a simple example. We have a silicon nitride on glass. So we see how it looks like the structure. We have a thick slab of glass and a thin, nanometric thin silicon nitride. And we see that the software, by using the transfer matrix method with a microloid formulation for optical coding and the net radiation method, can tell us what is happening to a ray that is passing from the top to the bottom. What we see is that there will be a reflection pattern in the spectrum, and is in dark red. Part of it will be absorbed in the silicon nitride. Then a part will be absorbed in the glass, and all the rest will be transmitted, and we see that in blue. Here I depicted the same color on the structure itself. We see that this is made for a quite wide spectrum from 300 nanometer up to 1200 nanometer. And we see that the sum of transmission, absorption, and reflection will add up to 1. Our simulation is performed under a set of assumptions. Let's see what they are. The interfaces between different layers will be supposed completely flat. Furthermore, we will not take into account any light scattering by any part of the optical path. The birefringent phenomena, especially the one of a foil, will not be taken into account. And however, this phenomena will be small compared to the large order that we are going to look into the next slides. Another assumption is about where the light source is. We have information about the P dot, and but we will not take into account its thickness, because we will have the light source exactly in the P dot, but just before the interface to the barrier. This way we don't have to worry about any light absorption in the P dot. We just need to take it right into consideration the fact that there is an interface, so going from P dot to barrier. Now about the structure. So what we're going to look at is the path of a ray from the P dot, as we said, all the way out. Now in detail, this would look like this. So we have a light source at this point, and we'll pass the silicon nitride, the OCP, again a silicon nitride, and then again an organic coating for planarization. And then we'll pass through a PET foil. Because of this, we need to know a few details about especially refractive index and absorption coefficient, but also we have to give some thicknesses. Now, it is not important for the kind of light we're going to use to have a thickness, because it's actually non-relevant, and also for the P dot, for the consideration we have seen before, is non-relevant to know how thick it is. All the other instead will be relevant to know the thickness, and especially for looking into the absorption. What we can say is we're going to look into a typical realization. So the silicon nitride will have thickness in the nanometer range, the OCP in the micrometer range, and this will be, all this material will be taken from a host baseline, and the measurement of refractive index and K has been performed in our labs. For what concerned the P dot and the PET, instead we looked into tabulated data. The spectrum of interest is then 400 to 800 nanometer, because that's where the light of this specific OLED material shines. Let's have a look at the results. We start looking at the consideration we can do on the angles of emission of arrays. So what we see here in the structure on the right is a series of rays and their angles, and how they are then brought outside through the structure. We are looking into the beam at 0 degree, which travels maintaining its direction. We see the beam at 30 degrees that will become the one at 45 approximately, and then we see also the lateral emission. It is interesting to look at the 45 degree emission, because there is a general requirement for display application. If we want to have a better insight on how the intensity at each angle is varying, we can have a look at the Lambertian graph. And in this Lambertian graph we see 3 curves. We see the red one, which would be the Lambertian emission just before the interface at the P dot, so really the ideal light coming out of the P dot. And then we see two cases. One, we call it the naked light source, and the TFE encapsulation light source. So what we see is that these two are very similar. We notice that the thin film encapsulator is slightly more directional, putting out more light at the 0 degrees. And when we look again at 45 degrees, which is here represented by this line, what we see is that there is really no difference. It's important to highlight this because the naked case represents from close a simple glass encapsulation. So meaning that between a TFE encapsulation and a glass encapsulation at large angles there is not much difference to be seen. Here are the results detailing the optical behavior of a bottom barrier. This details the transmission of a Lambertian emission from the P dot. The transmission over the spectrum of interest, defined as the SPW111 LEP emission, is always above 80%. The transmission even reached 94%. The transmission is though not exactly flat over the spectrum of interest. A natural question is if the LEP color will change by passing through the barrier. The answer will be given in the discussion slides. Now we have talked about Lambertian, but let's look at the angle. Indeed, this will be different from the previous analysis, which is mostly a consideration on basically energy. So we have an emission from one side that will be emitted in all directions, and we will see how much of this energy, light energy, will be transferred to the outside. When we instead look into a single beam, a single angle, then we really know what will be the spectrum like of this beam at the output. So we start with a 0 angle. So we can see that it's already a little bit different than the Lambertian emission. So here the peak is more moved towards short wavelength. If we then compare to the 45-degree tilt, like we see in this picture, we see now that the peak has shifted again to more of a red side, the red part, so more longer wavelength. Again, are we influencing the white because of angle of emission? We will see this in the discussion slides. So here we are at the discussion slides about colors. What we want to do is to evaluate how the white light changes if there is a transmission peak, or if this same peak shifts when the emission angles are different. The procedure followed is detailed on the Lightning Research Center site, which we have a link here below. And we can here on the right see the first result of this. We see a chromacity diagram where we have a color for each coordinate in the x and y dimension. And what we see are three small points close to each other, a diamond, a square, and a triangle. And this represents the three conditions. So a pure SWT 111, a tilted emission, and the emission through the barrier. Let's zoom in this chromacity diagram to distinguish better the color coordinates of a pure SPW 111 and the color obtained through the barrier and through the same barrier with a tilted angle of view. At this zoom, we clearly distinguish them. However, to know if a human eye perceives these as relevant difference, we use the CIE 1976 color distance technique. These distances obtained and detailed in this table are below 1, therefore are declared, according to the standard, non-detectable by human eye. We have seen that with a generic implementation of a structure, the color of SWT 111 will not be affected. However, a different emission of spectrum might react differently. For this reason, I would like to show here the possibility of tuning the silicon nitride layer thicknesses to achieve an almost flat transmission over the spectrum of interest. So, we are now at the conclusions. We have seen data for reflection, absorption and transmission, and we concluded that the barrier is highly transparent in the spectrum of interest. It is more than 80% and it peaks at 94%. For what concerns the angles of light beams, the TFE behaves like glass for the emission of angles. And looking at the color, the shifts are non-relevant for the white OLED that we took as input data. The original color of light is maintained and is not affected from the angles of emission. Of course, if the requirements will be more stringent, it's still possible to perform further optimization of the structure. We conclude therefore that our thin film encapsulation has not only excellent water barrier properties, but it is also an optically neutral layer for your OLED. I'd like to thank you for your attention, and we are available to answer your questions, and of course offline discussions are most welcome. Thanks again.